Well, welcome everybody. This is a Hacky Hour for the Centre for Safe Air. We've had a few of them before, and this is I think, the first one this year. And my name's Ivan Hanigan, and I'm collaborating with Cassandra Yuen on this particular um, uh, run through. And this one is about the Fire Smoke PM2.5 dataset that was created as a major project that the Centre for Safe Air and its predecessor, the Centre for Air Pollution and Health Research, CAR, have been pursuing. So I'd like to begin by acknowledging the country that I'm on, the WHOCC people and their elders, past, present, and future, and these other organisations that have made this work possible. And Cassandra for helping to run us through this. Now, this is a different kind of a presentation to what I normally give, and I think what most people come to the Centre for Safe Air to experience. This is a Hacky Hour, which is meant to be a fairly informal meetup where people can collaborate, learning and sharing insights about code and data and other research technical problems. So in that spirit, please do put up your hand, unmute, and ask questions. In the chat, ask questions that you think I or Cassandra or any of the other people in the room might be interested in or have an answer to. And so that's what a Hacky Hour is really about. As I said, it's also to give you an introduction to this Bushfire Smoke PM2.5 dataset. And in addition, we were very excited when we were planning this with the rise of using generative AI to assist with coding. So I'm going to have a bit of a discussion about that too. And so the outline of, I'm going to have to give you a talk about the methods behind the PM2.5 data creation and a bit on the validation of the dataset. Then show and tell section where we've given you access to pre-written code on GitHub and sent you instructions to how to set that up. So hopefully everyone can then run the example, and we'll finish with that discussion about generative AI. Now, because that show and tell part of the Hacky Hour is so important for everyone to share the experience, I want to make sure that you've got those links from the email and you are setting them yourselves up, and importantly, downloading the subset of the data that we're going to use today. Importantly, down the bottom there, you can see the password. So you might have clicked on that link in the email. You can see it again here on this slide down the bottom, and it's a password protected link. I'll explain a little bit about that in a second. But these other instructions, it's very important that you can access the code. Now, GitHub is great because it makes code free and available. But it's not something you can just start using willy-nilly without getting a bit of an introduction to it in its full featured kind of use case. So what it does do, though, is allow you to just click on the code button and then see this link to download zip. That's the easiest way to get the code. You just click on code and download zip. Store that somewhere, unzip it. That will create a folder that we've set up the code for you to run the analysis that was been pre-written, and that's where we'll put the data that you're going to run the tutorial with. Now, there's a few steps to getting that data, but I guess we'll have a chance when we do the show and tell to really make sure that you've got the data in the right spot, because code needs to know where the data is. So the code that we wrote assumes it is in a subdirectory called data provided. If it's not there, it won't work. Now, what we've provided you is only a training data set just for this particular Hacky Hour. It's only 2019. We want everyone to know that this data set is available for research. It goes all the way back to 2001 and it's been updated to 2023, and it's free for research use. All you have to do is ask the CARDAT team using this car.data email address or going to the website, I think that is clearly linked all over the homepage of the code to get that access to the data for your research. But in this particular, on today's session, you'll need to use that password, which is training_only. So there's a few chats. Cass, can you shout out to me if there's a chat question that out there from Cass? Hi, Jeff. Yes, this session is being recorded. Okay. So I'm just going to spend maybe 10 or, I don't know, 12 minutes, hopefully, going through this creation of the data. It's quite complicated, but what we've created over many years of effort now is this amazing PM2.5 particulate matter and indicative smoke from fires, probably bushfires. That was the aim. And it's really findable. I want to shout out to the ARDC, the Australian Research Data Commons. They put in a lot of co-funding for this, and we've been working with them to make all of CARDAT's data really findable on the Research Data Australia website. And here's a screenshot of it on the left. It's the first record when you search for PM2.5. And it has this paper so that's the data set that's been published. And then the paper that's been published that shows the methods and the peer review and everything like that. Whilst I'm talking about CARDAT, I just want to remind people who don't know about it, it's called the Clean Air Research Data and Analysis Technology, CARDAT, and it's been created by this Centre for Safe Air and the precursor CAR, and my own centre, the World Health Organization Collaborating Centre for Climate Change and HIA. So important points to note are that even though these two records talk about it finishing in 2020, it's recently been updated to 2023. That last 2021 to 23 period is also available. Also, a question I get asked a lot is, why is it just bushfire smoke? It's actually not. It's all PM2.5. That's a common misunderstanding because of the label, bushfire specific PM2.5. We actually had to estimate total PM2.5 to then estimate the specific components, which are due to extreme events, fires, bushfires, dust storms. That was the focus, because that's an epidemiologically relevant question. Not all PM2.5 is from these events. Here's an analysis of the Sydney data set. You can see our research on this goes back 10 years or more. And really, it's because it's hard to do the studies that just disentangle the effects of bushfire smoke from the ordinary background PM2.5, which is, as you can see, bubbling along day on day. You've always got a bit of PM2.5, and we know that's bad for you. Not really an interesting new research topic there, but these specific bushfire smoke peaks is quite an interesting question and of really potent public health importance. But getting on to how we created this, basically we do the combination of the observed data and a whole bunch of predictors, which are also on CARDAT and available. In particular, the NAPMD, which is hosted on a PostGIS server. Importantly, that's also got an API. So for the hackers out there, that's a really good way to get this National Air Pollution Monitor observational data set into your applications. And that's also available free for research. You just need to ask for the access. So then once we've got the predictors and the response variable, we do the prediction. This was done on a about 5 kilometer grid cell resolution. And then to decompose it into the fire smoke and the non-fire smoke, we did the seasonal trend lowest decomp, and then we validate. So I'm going to step you through those processes. Some of these methods might form the basis of future Hacky hours, because machine learning methods, particularly tree-based methods like this random forest that we used, are really becoming one of the most utilized tools in our toolkit. And this particular approach that we took, stepping through base models and then kind of feature reduction, data reduction, hyperparameter tuning, and getting the fully tweaked and tuned model, which performed really well. That's the R squareds that you'd be interested in up there on the left. Those R squareds are particularly good for PM2.5, which is notoriously difficult to get a good prediction for. And then the map, the mean and the standard deviation up there at the top, and you can see that spread. These are taken from the paper for that, so that's annual averages all the way through, and you can see that particular Black Summer event in ACT just spiking up there, which is a particularly problematic zone of the country down here in the southeast. So, seasonal trend LOS. That's a really cool tool. It's not new, it's been around for decades, and basically it takes something that's regular and seasonal, like this raw data set, and applies 3 decompositions. It applies a decomposition technique which results in 3 components: the regular seasonal part, the long-term trend part, and the remainder from those. So this is the error term from that simple model. And when you do this on daily data, the results end up looking pretty noisy. And there's a really good reason for that. It's because in a daily time series, with the day of the year representing very high resolution temporal increments, you can pick up things that are really regular in terms of the week of the year or certain seasonal parts, not just month by month, but also when the seasons change, there's regular climatic events. The weather happens to be regularly doing the same kinds of things around the same time of year. So in Darwin, this is shown here for 1 year. In the middle, May, June, July, the first week of June is often when the dry season fires start. And so you expect to get a spike. And so that green line, which is the combination of season and trend, that's what we expect. There's nothing really new about the first week of June being a high PM2.5 period. Before that, there's a steady increase through May, and then for some reason a drop off. There might be meteorological reasons, but regularly, year on, year out, the end of May, you'd see a drop. So these days that are above that are exceptional days. They're just unusual. And then when they are really high, either because they're high compared to any day or they're a certain distance above your expectation, which is sort of outlier detection technique, then we can classify them as extreme. And that's what we focused on in the discussion of the paper. So in a seasonal city with lots of wood smoke in winter, like Launceston in Tasmania, we can see that this is the days that are identified as being unusual. On the left-hand side, we're just using the 95th percentile, and you'll notice that that season plus trend is smoothed because we got a lot of feedback. People don't like seeing that spiky time series. They don't get it. But it makes perfect sense statistically and is actually really meaningful meteorologically. But for visual communication, we smoothed it, and we're going to talk a bit about that when we get to doing the show and tell. So standard kind of outlier detection method's pretty simple. Anything above the 95th percentile is one. That's on the left. This is saying something like, what is unusual given the total historical record? The 95th percentile, all 95% of the data is below that level. So these ones are unusually high. On the right, though, this is more of a statistical measure of deviation from the mean with standard deviations of the error term, so that remainder. And so the green line is actually 2 standard deviations of the remainder above the expectation, which is like being 2 standard deviations away from the mean. And so you can see slightly different days. That middle year wasn't really unusual seasonally. And so no days were flagged as being probably exceptional smoke in that middle year, 2006. Whereas using the 95th percentile, it's a bit cruder, and it was just like, that's the threshold. And sometimes people use 99th percentile, but the the two standard deviations is a little bit more like saying what's unusual given what I already know about the season and the trend that I expect. So here's another example in Sydney. You can see this is a much less seasonal town, and so the seasonality uh, classification isn't so important, and we're getting all these, and so this is a long time period with that exceptional black summer period. On the left, everything's above the 95th percentile, and likewise, it's exceptional given what you'd expect for that time of year. And I don't have time today, but there was a range of efforts we went to validate both the PM2.5 magnitude for the total and the events that we've identified as being probably fire smoke, either from wood heaters and extreme wood heater inversion layer events or bushfires, extreme landscape fires. And so what we were trying to do here is make additional flags and use additional machine learning approaches, classification and regression tree models, and got a whole nother presentation about how that's going. But yeah, we have a good sense of how this aligns with well-known bushfire events, which I published as a validated biomass smoke events database, which identifies if they're wildfires, prescribed fires, or dust storms or wood smoke heater inversion events. And my colleagues at the University of Sydney are working on that. So that was my 15 minutes of explanation. I really like talking about this project, so I could stop and take a few questions, but it is important as a Hacky Hour that we do get time for this practical hands-on session. So yeah, let's make sure that A, if you've got any burning questions, you've got time to ask them, and B, if you've got any issues getting yourself set up with the code and the data, that we can sort those things out. It'd be great to hear from you. This is an informal methodological training session. All right, so I'm going to step you through with what's on my screen. I've already downloaded it. It's about a 300 meg file, so it took a minute or two. And one of the things that I talk to people a lot about is that OneDrive on Windows kind of screws up some of the connections that data and code have. And so when I'm doing a data analysis project, I often really focus on putting that on my C drive. And so here's my particular projects for coding. And then I back it up to OneDrive once I'm finished. For some reason, OneDrive creates symbolic links and complicated paths and synchronizing and keeping offline copies of files. It doesn't really play that well with a serious coding project. I've downloaded the code and you can see that download zip file. I've unzipped the data into data provided. And so what you will have gotten from that link, that password, is Bushfire Smoke subset. This one is the 95th percentile for every grid cell. And this one is the standard deviation of the remainder for every grid cell. And we've gone ahead and created a bit of an example with what we think is, well, what we often get asked for is assistance to extract the PM2.5 data for particular study locations. Often these are the records of health study participants, so their residential address or where they were when they got sick. So I'm just going to go ahead and open up this RStudio project file. I won't explain too much about what's going on because we will probably have future hacky hours, and I think we've had a past hacky hour on the topic of getting to know your way around RStudio. They've updated it recently, so I just saw a message saying, do you want to update? I don't want to update. I've got this RStudio set up the way I like it. I like to have my console on the right and my code on the left. I often like to maximize them both, so I've just got code on the left and the output on the right. I can run line by line. If you don't already have Terra library installed, RStudio should be prompting you to install it. And likewise, data table is something that I recommend always getting loaded. RStudio is one of the most commonly used interfaces for R. There's a few things that I reckon should be advertised more widely, like this center console for going up and down the script, and the option to source the entire script, which I won't use today, but I recommend that people always make sure that a script can be sourced as part of their coding practice. So what's going on here? We're going to load up a CSV, which is the location coordinates, and that's been prepared um, by Cassandra and me. And what we're actually doing is just assigning these as paths. So that's just a text path, as is this. This is configuration type variables. And it's good to have a section at the top, as you can see, inputs, the definition of the inputs. And then you can use them with these functions. So read CSV is a function. It's gone and looked in the file location for the CSV, and it's loaded it, and this prints it to the screen. I think it'd be really exciting if people are interested, they run through the techniques of this particular example, and then try tweaking it to do your location of interest. Maybe it's where you live, or maybe where your grandmother lives, or maybe where someone in your study lives. And then you can probably move pretty quickly from that to tinkering around with it to do multiple locations at once. And you can imagine that as a health researcher, that's a very important thing to do because you've got a bunch of participants in your study and they all need the data attached to their locations. So I'm going to run through as it is. It was set to do Hobart, which is an interesting city, especially in 2019. And we're just going to do these lines, and I'm not hitting run each time, I'm hitting Control Enter. So what that did was assign those basically numbers to being a spatial object with a coordinate system, CRS, coordinate reference system. And that's really important when you're using spatial data. So now this line here that I'm running loads up a spatial raster dataset, which is a netcdf file. And that's basically become the industry standard for spatiotemporal environmental data that's gridded. You'll see that a lot in climate and air and atmospheric chemistry. All kinds of data are coming in netcdfs. And that's pretty simple. Does a good job of reading it in and telling you about it. Now what we need to do to replicate the analysis I just showed you is grab the 95th percentile values for every pixel and the standard deviation of the remainder. Now this is gotten to this the dates for the time period. We're going to choose a particular study period late in 2019, which was interesting because of the massive fires. Line 52 is just selecting a particular layer, which is there for every time period, time point. And so I'll show you what I mean by that. It's taking out the times that we're interested in and the layer we're interested in, because there's multiple layers in that netcdf file. And this line will plot it to the screen. Takes a little while. I'm opening up my plots console. And it should go all the way to the 25th of December. Happy Christmas. These pixels are shaded with this legend, so that's PM2.5 total. Per day for 5 kilometer grid, so pixels there for the whole year of 2019 and available to you all the way back to 2001 and currently up to 2023. Okay, so moving on to, I'm just going to check any questions. I hope everyone has got code and data, and the RStudio might not look like mine because I've configured it to have this setup, but it should be working for you. I like to have my plots open and my code as I go. So I should say this is an interactive programming session rather than the kinds of data analysis that a lot of people do, which is more about creating a pipeline of steps that go through every part of the analysis. That's why I said at the end of programming, it's good to click on the source button, which runs the entire script, but other people set up subscripts and modules, and it all calls each other and is a very rigorous and robust way of writing code, as well as writing functions that use techniques of speeding things up and making things really easy to maintain. This is a style of coding which is really useful for exploring data and describing it and doing visualizations and tests. And so I just wanted to make that point too. So you can see the comments are really clearly saying, well, what are we going to do next? We're going to replicate that plot from the paper. And we've already got the study location in mind, which is Hobart. We're going to define a list of these variables to get. And here is a function. You can see it's defined as a function inside lapply chunk, which means for each of these variables, we're going to run this function, which is to grab the raster data set, extract the raster data for that location, turn it into an easily worked with data frame, assign it names, and return the value for each of those. So running that, this takes a little time for one location for all of these variables. As you go up with more and more variables, more and more locations, this will take longer. And so there's probably a different technique that you'd use again with parallelization and multi-threaded compute to make that faster. But it's finished in the short time it took me to blab on about that. And this function is going to put them together by date, giving us an output data frame. And then we're going to assign the 95th percentile for that grid location. That's a single statistic for that location, as is the standard deviation of the remainder. And so every day has that attached to it. And we can then see the structure of this. Got the 365 days of that year. These variables that were extracted for that location, which is the Hobart coordinates that we selected. And it actually appears that what I've got here in Smoke 95 and Trimmed Smoke 2SD is actually a flag of whether or not it was above or below that level, zeros and ones. So the one is saying that that's above the threshold that we've set. Hi, Will. Been doing exploratory analysis. You want to look at bushfires and heat waves? Yep, all really good questions. And I might put them on the back burner rather than just get to the bottom of this and then we can launch into them. Will, giving me motivation to speed up. um, this is the plot of total PM 2.5. That was the summary. Will, you've identified some negative values. This particular location doesn't have any, but they're not fatal. We do expect them, and there's good reasons for them and simple ways to deal with them. Now, this one is that blue line. That's that spiky season trend expectation, and so it's really interesting. I'll zoom in on this one. In Hobart, this first week of July seems to always be a bad smoke week, and so it's not exceptional. It's a little bit exceptional in 2019, but it's not hugely so. It's just like, oh yeah, it's the first week of July. That's always smoky in Hobart. For whatever reason, maybe it's a particularly regular climatic event that happens in the Southern Ocean. But obviously, I said when we're workshopping this, a lot of people don't like seeing the spikiness. It just doesn't make sense as a seasonality thing. And so we don't use it that much for visualization. But we did use it for the flags because we were hoping to use it as an outlier detection tool. That's the 95th percentile. That's those dates that are flagged as being above it, and that's your legend. Same thing with the two standard deviations. It's called trimmed because the 2019 and 2020 PM 2.5 remainders were so vast, we had a problem with the standard deviation, so we trimmed it. So it's like taking a trimmed mean in an in econometrics, they do trimmed means for this purpose too. And those are the dots for days that are above the expected 2SD. Now, at the bottom of my script, I've got some stuff that I wrote to demonstrate using generative AI. But Will, do you want to actually unmute and talk us through your questions?
Yes, thank you. Thank you, Ivan, Cassandra, and hi, everyone.
Welcome.
So, just a context, I'm doing research in my PhD at ANU, and the topic is about bushfires and what is the intersection with heat waves and the impacts on health. So, I was working the last days playing with this dataset, the version of bushfire specific PM2.5 Australia from 2001 to 2020, version 1.3. So, and I realized there are a couple of the features like I would like to know more about this. For example, and there are some when this variable PM2.5 predictions have some negative values. So I was thinking like how we should analyze, understand this observation, this value when it's negative. And also there are some days there is no data, there is no value. So I was thinking why is the reason of that? If it's estimation, right? Yeah, according to this methodology, it should be estimated for all the days, but I would like to know more about this. And then also, the second question is when we understand we want analyzing this variable, it's only the PM 2.5 is only from the smokes, or also we should take into account like it's coming from other sources from the pollution. And finally, it's like I was thinking like this data goes only up to 2020, but I think at the start of the session you mentioned like there is the data can goes up to 2023. So I would like to know how we can access to that the last these 3 years more of data if
Yeah,
it's possible. Yeah.
yeah, that's exciting. We just released the update. Um, so I'll go backwards into your questions because that's the easiest one to answer. You just ask for it the same way that you asked for the main data set that you got through the CARDAT data access form online. The second question is pretty easy to answer as well. This is total PM2.5 as the base response variable. It's monitored and it's observed. It is the total PM2.5 in the air from any source. So that's what PM25 pred is. It's the predicted total PM2.5. Then we have gone to all this extra effort to try and decompose it and figure out, well, what is the source of this? What's likely to be bushfire smoke or wood heater smoke? Because they're actually theoretically fairly easy to disentangle because wood heater smoke always happens in winter and bushfires often, the big bushfires happen in summer. But it's not that simple. And so we went to all this extra effort and the manual validation process that I can tell you about later. But you should just, if you're not focused on this, the source of extreme events, you can just treat it that grey line. That's just daily PM2.5 from any source. Now, there's two parts in your first question. The second is easier to answer. Missing data is there for the days where we're missing a predictor from a satellite. It was about solar radiation. Cass will pick me up if I'm incorrect there, but there was a few days with a missing predictor. And so you can't do a prediction on those days, and there was only a very, very small number of them. And there's heaps of techniques for filling up missing data. You can take the average of the day before and after. That's not going to cause too much of an error. You could do some kind of smoother. You could do some kind of um, automated moving average approach. What I'm trying to think of is auto-regressive integrated moving average, ARIMA. That's one they like to use in forecasting models. But yeah, you can just fill it up or drop them. They're just missing data. With the negatives, there's a huge range of reasons why there's negative data. There's negative data in the observations, but that's probably not the cause of what you're seeing. There can be negative data estimated because predictors that are the rules that are trained out of the data can lead to extrapolations away from the limits of the data that were used for training the model. I suspect that's what's happened. Cass, did you come to any greater insights than I have right now?
No, I think that was where we got to.
And they just mean really small values. Whatever's the training was, if it was really low or if it was a valid negative, it's actually a really, really small value. And when you predict, all of the predictors are saying this is going to be really low. So there's two often used approaches. One is just to set it to zero if that's a meaningful thing, but PM2.5 you're pretty much never going to expect to have nothing. So statistically, you choose a really low percentile, like the first percentile, and say in this location, there's only like 99% of the data is above this value. And so I think this really low value is above that. Maybe we should ask the generative AI actually. It's a good use of it. So what I did was grabbed my favorite generative AI tool, which is called Claude. And I grabbed this first bit. So I'll show you exactly what I did. That's the record of my chat. So at the end of doing this, I started a new section of my script and I looked at the data and I thought to myself, well, everyone tells me they hate the spiky STL. I'll get Claude to tell me how to quickly and easily smooth it so that it's more visually appealing. And so when I looked at the structure, I said, okay, here, I've got this particular thing. Claude will want to know that. And I copied it and pasted it into a little bit of text. And that was my first prompt. And here it is. Good morning, Claude. I've got this data set, these two variables combined, showing the STL. And it was really spiky. I want to smooth it. Also, importantly, only use base R graphics. I get really sick of over-complicated ggplot2 graphics. And Claude came back really sensibly and said, good morning. I can help you with this. First of all, have you thought of a moving average? Option 1. Hi, Sylvester. No, season and trend is obviously your expected value in that season given that trend. We can talk about the expected component of bushfire smoke later, but it's really important. Season trend analysis is trying to predict what it would be expected to be in that season given that trend. And so seasonal component, this moving average, actually ignore the moving average. It's much more interesting to use splines. This is a locally weighted smoothing spline. And then there's I believe this will be a cubic spline of some description. But it got me this one, and I copied the code. Actually, no, I didn't, because I realized I don't have a variable called day of year or seasonal yet. I've mistakenly given it too little information. And it picked this up too. It said, can you share the names of those variables in your data set so I can help you with your code? So then I went back to my thing. I looked at the data. I copied the thing. I wrote down the next prompt. And I said, these are the variable names for these three variables: date, seasonal, and trend. And it's gone, okay, well, let's just look at low S. It's recommended. It's a really good technique. And given me this code. It's also gone ahead and given me the other two options and then explained why some of the details. So I was able to go, well, I do like low S. STL is based on low S. So I copied the code and I pasted it straight into the console to check that it worked. It did work. So then I pasted it into my script and thought, oh yeah, that's not too bad. However, it's not exactly what I want. That's saying this is the STL. So Sylvester, that's exactly what you were asking about. That's season plus trend. That's actually that's not the data, which is what we like to have to start with. So then my next prompt was, actually the raw data is called PM2.5 pred. I want a plot that shows the raw data as a light gray line, and then that spiky STL is a green, and then the smooth version is blue. And it gave me the code that did that. I copied it, checked it, worked. I'm not interested in its alternatives. And I think I've modified this slightly. I think I went with black instead of blue. And I added the two standard deviations. Oh no, I kept it as blue and I added the two standard deviations above it as black. And this is what my colleagues prefer to look at when they're talking about seasonal components. That's a very smooth season through the year. This is two standard deviations of the error from it. So all of these grey lines, which are the actual PM2.5 from total sources, is above what we would expect. And the amount that it is above the blue line, to your question, Sylvester, we think that amount may be in large part due to the source that we've identified. In this case, it's probably wood heater smoke. Back here at the start of 2019, there was a big bushfire in Tasmania. They didn't get the 2020 summer fire. They got one earlier. And you can see that that's been picked up here on the left-hand side. And so every day that's above this threshold, we think it's likely to have been caused by the bushfire. And so the component the difference between this or some level above the expectation, that's the anomaly. And that could be the component that we're talking about is bushfire smoke. So to your question, Will, I just had a chat with Claude and start off very sociably. It's quite a clever thing. Well, before I get to that, actually, I've got a slide and a story. So we just did this show and tell. This is the icon from GitHub. He's cute. With generative AI, coders are using it all over the place, and the later the version, the better they're getting. This particular example caught my eye. This senior software engineer with more than 30 years experience was explaining in a Reddit chat that got advertised on LinkedIn. They'd spent more than 200 hours debugging this bug over 4 years in a piece of code that they'd refactored, and it had introduced an edge case that was a bug. He could never track it down. He called it his white whale. It was the thing that he could never find. And he tried these other AIs, and they couldn't solve it either. But then the latest version of Claude came out, and it solved it in 30 prompts. And it made him feel humble and really amazed. It understood the architecture of what the whole software was trying to do, not just the code line by line. It understood the design level logic. And there were 60,000 lines of code that it had to absorb and look through. And then in those 30 prompts, he had a chat with Claude and it figured out this deep system problem. Now that's great and probably okay if your code is open source. Any problem that you're working on that can be openly discussed is going to be fine because Claude and the other ones learn from this information. It may not be safe to put closed source intellectual property in there because obviously it could become the answer to someone's future question. But also just the veracity of the information can be questioned. And so this flowchart is quite useful. When might it be safe? Does it matter if the thing is true? No, then it's safe. Otherwise, yes. You have to go, do I have the expertise to verify that this is accurate? If not, you're not safe. You have to know enough about what you're doing and be able to access the resources, the reference material, books, experts. Do you have access to expertise that can verify if that is accurate? If yes, are you now willing to take responsibility, legal, moral, and the time it takes to do the checks to verify that? If not, not safe. If yes, it's possible, go ahead and use it. ChatGPT or Claude or anything. But you still want to take the time and verify potentially every word and sentence or piece of code or statistical advice has accuracy and common sense in it. So with that in mind, I'm going to have a chat about negative values. In my data set, it has predicted PM2.5, and I'm surprised when values are negative. How far negative do they go? Will, is it like 5 or 10?
Well, I make a spatial average, but it was during the spatial average by different sectors was like -2, -3.
Yeah, around -2 or -3, that's about right. And I is not plausible. Give it a fair amount of information about what you're thinking because the chatbot is designed to have a chat. It's not, hey, robot, do my homework for me. It's like, hi, good morning, friendly robot. I'd like to have a chat and a conversation about this topic. I've been thinking about what to do. You don't have to, it does understand incorrectly spelt words, but would like to chat with you for ITs. And then what goes and thinks. They're physically impossible It's simple truncation at 0, and that's the code to do it. Like I said, 0 is also an implausible value for PM2.5. So what else have we got? We could try to use observed data in the location and recalibrate that. So you could go off and find the closest monitor and find out on that day what was a value close to where my prediction is. We don't have very modern monitors. We could have done the modeling differently, say on the log transformed data set, which can't go negative. And so when it's back transformed, it would not be negative. That's a good idea. But you can't do that because we already ran the model on a supercomputer. You could flag them, interpolating the values as if they were missing. You could just remove them and say, let's interpolate them using like I said, the average of the day before and the day after, which is a simple way to fill up some missing data. And there's some code to do it. And then it's wanting to have more of a chat with me. But actually, it didn't come up with my. I sometimes like to limit the values to the lowest end of the range observed in that location. What do you think? And so you can explore your ideas, and it usually says nice things to you because it's a friendly robot. And so you've got to be careful about confirmation bias there as well. So it's a very sensible approach using the observed minimum as a floor. And so that would be location specific. You might be able to get lower in a remote part of a forested area than you're ever going to get in a built up residential zone. So you'd use that pixel and say, what's, like I said, the first percentile in this pixel. And that would be higher in a residential zone than it would be in a forest. Physically realistic, scientifically sound, use some implementation, even better. Not the actual limit of the data, but something like the lower percentile, 5th or 10th, or like I said, 1. This is based on statistical, scientific judgment. Let the data distribution inform you, because that lowest value might be itself an outlier. Now, when you get a response that agrees with you, it's often good to play devil's advocate. I'm keeping an eye on the time. I've got virtually no time to do any more, but I like doing this. It turns it around. You start a new chat so you don't have the context, and say, in my study, I have negative values and I want to set to a positive. And playing devil's advocate, I don't think that the lowest 5th percentile is a good approach. What do you think? And so this approach kind of protects you from it starting to agree with you and just reinforcing what you already believe, but you may have not thought of it, all the ramifications. And so you're challenging that. And so it's come back with, good question, can be problematic because of arbitrariness, other relationships in the data. These other ways could be better, which we've already excluded because they're impossible. And I've explored a bit more, and I understand a bit more about the implications of my approach there. And then I would also have a statistics textbook that I can confirm with as well. So Sylvester, did that answer your question? You want to unmute and talk about your question a bit?
Yeah, thank you.
Hi.
Hi. Yeah, thank you. Yeah, thank you for the presentation. That's a nice one. Good job done.
Thanks.
Yeah, just a quick one. Because actually I'm just not too clear about if there is actually a concentration value for the bushfire in the data set instead of just categorizing a day as being a bushfire day or not. So that's the reason I was thinking if the seasonal peak is being quantified and I assume as the bushfire, or how do you actually have a variable which actually capture the bushfire concentration in the data
So
set?
in our published work, we have done that. We've identified those days and we've calculated the difference between the actual level of PM2.5 and what would have been expected if it wasn't abnormal. And we've said that is the amount of bushfire smoke.
The bushfire, okay.
That's the approach. And it's been published, it was peer reviewed, but it's not perfect. There will be false positives.
Yeah. Of course. Yeah.
Statistically,
I saw the paper. I read the paper anyway. So I just want to be sure that if I'm actually picking the right information or I'm misinterpreting it. So
yeah,
that's fine.
That's right. Yeah.
Thank you.
Great. Well, we've got come to the end of the hour of hacking. So have a hacky hour of your own. Enjoy your relationship with your new friendly robot. And don't forget to reach out to car.data@sydney.edu.au for any questions or data requests can go through the CARDAT website. Thank you and
Bye.
see you later.
Thank you.
Thank you so much.